Okay, so is this tracking me? It's going to be one of those days, huh? Let's see. We had a number of people. It's turning the paper it's sitting on. We had a number of people absent last period and this period, so we're going to try and keep a record of this. It's an important day. Okay, where are my notes? All right, guys, so 14.3 is what we're going to cover today. We covered 14.1 and 14.2 yesterday. Okay, so guys, just to put this into a framework, what we're talking about today, yesterday we spent the whole day on calculating the rates of reactions. So if you have a certain reaction, we have concentrations, and we focused on plotting, like figuring out what the rate of the reaction is, okay? So now we're going to be using that data, different reactions having different rates, and we're going to use this data to figure out a general rule that describes how the concentrations of your reactants can affect your rate. So that's what we're focusing on today. So how does concentration affect rate? All right? Before we kind of dive too deeply into this, I want to introduce, there's two different types of rate laws. The first is the differential rate law. You guys are going to just, whenever I say just the word rate law, I'm referring to the differential rate law, so you might just hear it as simply rate law. My door is open. Can someone get that for me? I don't want to get recorded with whoever that is. It's a minor, I'm sure. Or did we? Hi.
This is for Jeremy.
Okay. Can you pass that back to Jeremy? Thanks. Okay.
Yeah.
All right, guys, so our differential rate law tells us how the rate of the reaction depends on the concentration of the reactants. Okay, that's what the differential rate law will describe for us. It'll do a mathematical relationship between concentration and rate. The other type that we're going to be talking about tomorrow is the integrated rate law. Whenever I mention integrated rate law, I will say the whole thing, so I'll say integrated rate law. So if you hear just rate law, that's the differential. So it's the integral. And yes, I did email Mr. Taylor about all the stuff that we're talking about, so he can apply it in your classroom if you want to. So you might be seeing chemistry and calculus pretty soon. Let's see, the integral of the differential rate law. So it's the integral of the rate law above. Okay, so we find this rate law, and then we take the integral of it. Okay, and if you don't know what an integral is, that's okay. It's your understanding of this chapter does not hinge on that. You'll just be able to see the equation and use the equation as is. You won't have to understand how we got there. But if you know calculus, I can show you guys how this is done tomorrow. And what it does is it expresses how concentration depends on time. Okay, so I really want to stress the difference between these two guys. The differential rate law tells us how the rate depends on the concentration. Once we have that rate law in our hands, we can integrate it and then use it to figure out, okay, for a given reaction at these concentrations, what will be the concentration at 200 seconds from now? We can actually predict what concentrations will be at certain points in reactions just using an equation that we get. So we won't have to rely on experimental data anymore. Okay, but we'll save number 2 for tomorrow. We're going to focus on number 1 today. So we're going to dive more deeply into this differential rate law now. So I'm going to put differential in parentheses because really you're just going to hear the word rate law. You might also hear it as the rate expression. It's the same thing. So the format of it looks like this. This is something that you would box in your notes, okay? So this is called the rate law. This whole big thing all chunked together, that's the rate law. Yesterday we talked about this part of it. We talked about the rate. What are the units always on rate? Molarity over seconds. Okay, so remember always, 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 always the units on rate will be molarity over seconds. Okay? This is called your rate constant. And the units will vary on this. I'm not going to tell you right now what they are because they'll change depending on what your equation is. So units vary. A and B are concentration of the reactants and then N and M are the reaction order. These numbers usually are they're usually going to be 1, 2, or 0. That's the most common numbers that you'll find for N and M. And the only way, I'm going to stress this is very important, the only way that we can determine what N and M are from experimental data. There's no way to just look at a reaction and just tell. You have to look at data to figure those out. We're going to practice that today. So determined experimentally. Okay, so that's what the rate law is. Are we okay back there? Yes? Okay. So let's practice finding these things. Do we have any questions so far? Have I confused anyone yet? Okay. Okay, so what I want to show you guys is this. You don't have to copy this data into your notes if you don't want to, but you can just reference it. That's on the board as it is right now. So this is data for the reaction above. Okay, so when Na reacts with Cl, it creates NaCl. So the rate law for this reaction would be rate is equal to K times the concentration of Na times N, or to the N power, times the concentration of Cl2 to the M power. Okay, and our job is to figure out what the numbers for N and M are. Okay? So let's try and figure that out. So the first thing we're going to do to determine the rate law what this is called the method of initial rates, is what we're going to be doing. So we're going to take a look at this data. Okay, so if we want to find N, so let's just focus on figuring out what N is. To find N, we're going to figure out two trials where this term doesn't change at all. Okay, so in what two trials does the concentration of chlorine not change? 1 and 3. So we're going to put trial 1 over trial 3. Okay, so and again, the whole reason is because we're trying to figure out, okay, when we change the concentration of Na, what effect does that have on the rate? So let's plug that in. So we're going to put trial 1 over trial 3. So the first thing I'm going to do is put the rates over each other. So for the rate for trial 1 is 0.340 molar per second. And then the rate for trial 3 is also 0.340 molar per second. And then I'm going to apply the rate law here. Okay, so this is equal to the concentration of Na for trial 1, which is 0.300 molar to the N power times the concentration of chlorine, 0.430 molar to the M power. That's trial 1. And then down here at trial 3, the concentration of Na is 0.15 to the N power, and then Cl doesn't change, it's still 0.43 to the M power. And now we're going to solve for N. Okay? So the quickest, easiest way, I'll let you finish copying this. The easiest way to do it, okay, let's take a look. So these two terms cancel out, right, because they're the same. This divided by that's going to be 1, so we can cross this guy out. And now let's do some math. So this divided by this, what's this divided by this? 1. Okay, so 1 is equal to, what's 0.3 divided by 0.15? 2. And if that was hard for you, cover up the decimal points. What's 30 divided by 15? 2. Okay, that makes it even easier. So this is 2 to the N power. Okay, this is where math comes in. What? 2 to the what gives you 1? 0. So that means N is equal to 0. Okay, so this tells us so the reaction is 0 order in Na. So the reaction is 0 order in Na, okay? So what does that mean? That sounds like a bunch of fancy words strung together, but it means something really simple. If something is in 0 order in Na, that means, and the data supports this, take a look. If we change the concentration of Na while these remain constant, what happens to the rate? Does it change at all? No. So if something is 0 order, that means the concentration of that reactant has no effect whatsoever on the rate. Okay, so we can do whatever we wanted to the Na, and the rate wouldn't change. That's what that means to be 0 order. Okay? All right, so now we know what N is. When we plug that in, it's going to be 0. Okay, so now we have to find M. So we're going to do that next. So to find M, yep. This part? This. Here. This? Here. Nope, sorry. Gosh. Here? So I'm applying this to each part. So this is the concentration of Na to the N power, and this is the concentration of Cl to the M power for trial 1. What happens to the K? The K we're ignoring for the moment because the K just stays K. Like, we don't have to figure out the math of it yet. We have to basically know what N and M are before we can find K. So we will be finding K after we find the whole rate equation. Okay? So you can ignore the K and just plug in those parts. Okay, so let's find M. So, okay, so if we're going to try and find M, M is the coefficient, I'm sorry, the exponent on the chlorine. So we're going to try and find two trials that the sodium doesn't change. Okay, so what two trials does the sodium not change in? 1 and 2. All right. So if it's 1 and 2, we're going to take a look at this. Now, I'm going to give you guys a big hint here. When you're setting this up and you want to put trial 1 and 2 over each other, take a look at their rates. Whatever has the bigger number, you should put on top. It'll just make your numbers easier to work with. Okay, it'll just see how that was a really obvious answer. The answers will be really obvious if you put the bigger rate on top. Okay, so what we're going to do then is do trial 2 over trial 1. You could still get the right answer if you did it the other way, but this is just going to be neater. Okay? So we're going to do the same thing. So trial 2 over trial 1. So the first thing, we put the rates over each other. So the rate for trial 2 is 1.360 molar per second, and the trial 1 is 0.340 molar per second. Then I apply my rate law. So for trial 2, let's see, for trial 2, my concentration of Na is 0.300 molar to the N power, and then my concentration of chlorine is 1.720 molar to the M power. Trial 1, my sodium is still 0.300 to the N, and my chlorine is 0.430 to the N. Okay, so now I've got that plugged in. So if you notice, what can we cancel out in this one? These two terms, right? They're the same. So we're going to cross these guys out. And now I just do basic math. So this divided by that is what? Anyone got it? It's a simple one. It's 4. Yeah, so this divided by that is 4. All right, and then this divided by this also happens to be 4. So this divided by that is 4, and it's going to be 4 raised to the M power. Okay, so what must M be if 4 to the M power is 4? 1. Okay, so now M is equal to 1. So this means the reaction is first order in Cl2. Okay? So the reaction is first order in Cl2. Okay, so what does that mean to be first order in Cl2? So what that means, guys, is that if you take a look at what happened here, we quadrupled the concentration of chlorine and the rate quadrupled. Okay, if we had doubled the concentration of chlorine, the rate would have doubled. If we had tripled the concentration of chlorine, the rate would have tripled. Okay, do you guys see that relationship? And we don't have a second order example out here, but if for a second order, if you double the concentration, your rate quadruples. It's a square relationship. So if you're doubling it, what's the square of 2? It's 4, so this would quadruple. Okay, if you triple it, what would happen to the rate if it were second order? What do you guys think? 9 times. It would increase 9-fold. Okay, you just square whatever the whatever you did here. So if you tripled it, then the square of 3 is 9. So the rate would increase 9 times. Okay? So anyway, now we have our answers for N and M, so we can plug that into our rate law. Let's see. So this is what we've got. So our final answer for our rate law looks like this. Rate is equal to K times Na to the 0 power times Cl2. And we don't write ones, so that's just what it looks like. Okay? If anything's ever to the 0 order, though, you can just ignore it. So you could also write, both of these would be correct, K is equal to Cl2. And just ignore the Na altogether, because it's just going to be 1. Okay? So both of those are correct. We can flat out ignore that because it's the 0 order. It doesn't have any effect on the rate. Have I lost anybody? Are we following? This is pretty okay so far? Yes? Okay. All right. So again, I solved M was 1, and that's why there's a 1 here. And I solved N was 0. That's why I plugged that in. So the last part of this, today is a pretty short day in terms of notes, is finding the K value. So we've done everything for this rate law except for what K is. Okay, and K is just the constant that relates how the concentration relates to the rate. Okay, it's like the hinge pin that connects them both together. So finding K is very simple. You just pick any trial, and then we're basically going to plug and chug. So I'm just going to, for this reaction, I'm just going to pick trial 1. And I'm going to plug in my data for trial 1 into my rate. So my rate for trial 1 was 0.340 molar per second is equal to K times the concentration. I'll plug in the Na for kicks. molar to the 0 power, and then the concentration of chlorine was 0.430 to the first power. Okay, so now all I did, guys, was just take the data and plug it into my rate equation to set this up. Okay, from trial 1. And the idea here is that we're solving for K. So now we just have to do a little bit of math and figure out what K is going to be. So to do that, what I'm going to do to get K alone, I'm going to bring both of these terms over to this side. So that's going to be 0.340 molar per second divided by 0.300 to the 0 power. That's molar. Doesn't matter. Times 0.430 molar to the first power. And that's equal to K. This term ends up being 1. Okay, so if it ends up being 1, I'm going to just write 1, and then 0.340 molar per second is equal to 1 times 0.340 molar is equal to K. And so doing this math out, then I'll get 0.791. And now is the big important thing. How the heck do we figure out what the units are? What are we going to do? What are the units on this? S inverted. Very good. Okay, so if you see molar is on the bottom, and we have molar on top, these two will cancel out, so we're going to have a per second left. Okay, so the way we write that in science is S minus 1. If you guys have ever seen that, so if you ever see it per second, it's the same as writing S minus 1. Okay, so this is going to be the K value for this reaction.
Don't you have another M left over from the 1?
Because it's to the 0 power, no. And I don't remember why it gets rid of it. There is a reason it gets rid of it. It's because it has no effect whatsoever. So really, it's not even considered. Yeah, so it really should just be left out. But there that is. So for all, this is actually going to be the unit of K for all first order reactions. Okay, so there's that. So that's how you find K. Pretty simple stuff. Questions so far? Feeling good? Okay. So the last thing I want to tell you guys is how to find the units if we're not working with a first order reaction, and then we'll be done for the day. So the notes are pretty short today. So units for K. Okay, so we just did a first order reaction, but what if we had a 0 order reaction? Okay, for a 0 order reaction, the rate law would look like this. Rate is equal to K times the concentration of A to the 0 power, which is 1. So really, essentially, it's the rate equals K times 1, which is just the rate is equal to K, essentially. Okay, so to find the units on K, it's going to be really easy. What are the units on the rate? What are rate units? They're always going to be what? The same thing. Molarity per second. So molarity per second is equal to K. We're done with that. Okay, that's 0 order K units. You guys remember yesterday I told you you might see it in a little bit of a different form. What other form might you see it? Moles over, yep, so moles over liter seconds, because molarity is moles over liters, right? So you might see it in this form as well. Okay, so there's 2 ways you might see it. Okay, I'll reiterate, I'll do it with this method for a first order reaction real quick too, just so we have it in order. So if you had a first order reaction, you'd have rate is equal to K times the concentration of A. And so just applying the units, just like pulling the units out, leaving the numbers behind, the units for rate are molar over second equals K. And then what's the unit for concentration? Molar, right? So capital M. So to isolate K by itself, what are we going to do? Divide by molar. So we're going to have molar per second. Well, I'm going to leave the molar on this side. Molar second equals K. All I did was divide the molar and bring it onto the bottom down here. Okay? And then these guys cancel it out, which is why we have S minus 1 is the units for K for first order reactions. Okay? It looks a little bit neater if you draw it without numbers. Second order. There's a couple ways that you might see a second order rate equation. You might see it like this. Okay, that could be a second order rate equation. Or you could see it like this, where you add up. Did I tell you guys the overall order? Did I skip that part? I think I skipped that part. So for your overall rate equation for an entire equation, you add up the individual orders of the reactants. So A is first order and B is second order. So they add up so the overall order is second. So if this were the rate equation for a certain equation, it's first order in A and it's first order in B. So the entire equation, you add up the orders so the overall order is second order. Okay? Just keep that in mind. All right, so in any way, this is the second order equation too. So both these are second order. So to figure out the rate, or for the units on K, you would put molar over second for the rate is equal to K. And what would molarity times molarity, what would that be? Molarity squared, right? Molarity squared. So then we would bring this underneath, so then we would have molarity times molarity squared S equals K. And this is where our vast knowledge of exponents comes in, because I know all of us are so strong on those, right? So for exponents, what do? When we have this over this? Subtract, right. So there's an invisible 1 here, right, that we don't write because it's just 1. So what's 1 minus 2? Negative 1. 1 minus 2 is negative 1. So then our units are going to be M minus 1 S minus 1 is equal to K. Okay, so those are always going to be your units for a second order equation. Here's a tricky question. What would if you wanted to use molarity, like the definition of molarity instead, how would that look? Liters over moles, right. So you might see this as liters per mole, because that's molarity flipped upside down. This is just molarity flips upside down. This is molarity flips upside down, and then you still have the S on the bottom. So you might see that as well. Okay? And the last one, I know you guys are like glassy-eyed by now, but one last unit, and then I'll let you guys practice this. People were freaking out about doing third order by themselves yesterday, or last period, so I'm going to teach you how to do it here. So the rate is equal to K times A to the third. That would be a third order reaction. There's a couple other ways you could arrive at a third order reaction. You could also have rate equals K times A to the second times B to the first, or K times A times B times C. Okay, so all three of those are third order rate equations. Do you guys see how I got that? You just add up the orders. Okay, so these are all third order equations, so the rates of K will be the same for all of them. So figuring that out, we have molarity per second is equal to K. What's molarity times molarity times molarity? Molarity cubed. Okay, so this is starting to look repetitive, hopefully. So now we're going to bring the molarity on the bottom, just like we did in the other problem. So molarity equals molarity Q times seconds, and that's equal to K. So now we're going to do the same thing with the exponents. What's 1 minus 3? Negative 2. So our units then are going to be molarity minus 2, S minus 1 is equal to K. So those are your units for third order reactions. And you might see it with the molarity written out. What would that be? Any clue? Liters squared over mole squared, right. So you might see liters over mole squared per second. Okay, so that's one way you might see that written. We're done. Okay, so I know this looks like a lot, guys, but really once you practice it, it will all make itself clear, I promise. All right.